discuss urban ground subsidence, which is a serious geotechnical engineering problem affecting many cities around the world. As shown in the diagram, ground subsidence happens when too much groundwater is extracted from underground soil layers, especially soft alluvial soil or fine-grained sediment. When the groundwater is continuously removed, the soil becomes compressed and loses its ability to support the ground surface. As a result, the land slowly sinks over time. This issue becomes more serious in urban areas because heavy buildings and rapid urban development place additional pressure on already weak soil condition. Because of that, urban ground subsidence has become a difficult challenge for civil engineers, especially in densely populated cities. For our case study, we selected SEMARANG, JAKARTA in Indonesia, where civil land subsidence have become a major urban infrastructure crisis. Based on the image shown, some areas are sinking up to 15 to 20 centimeters every year due to excessive groundwater extraction and rapid urbanization. These effects of the issues can already be clearly seen in many affected areas. Some buildings have started tilting and cracking because the ground underneath is no longer stable. Roads and drainage systems are also damaged due to uneven ground settlement. In coastal area, ocean water has reached seawalls because the land level continues to sink below sea level. This causes severe flooding, especially during heavy rain and high tides. This image shows the reality of how ground subsidence is affecting infrastructure and daily life in DC. As shown in this image, urban ground subsidence has created serious challenges for civil engineers because the damage affects many types of infrastructure at the same time. As the ground continues to sink, buildings, road and drainage systems become unstable and more likely to fail. Damaged drainage system also make flooding worse because water cannot flow properly during heavy rainfall. Besides, infrastructure damage, this issue also affects public safety and economic activities. Flooded roads disrupt transportation, while damaged buildings increase safety risks for nearby communities. Therefore, urban ground subsidence is considered a complex engineering problem because it involves geotechnical instability, environmental impacts, infrastructure failure, and human activities happening together. That's all from me. Thank you.
The group that involved in societal concern is the role of engineers. Civil engineers are responsible for making sure building, roads, drainage system and other infrastructure are safe for the public. If engineers fail to study soil condition properly, then subsidence can become worse and cause floods, building crash and road damage. So engineers must always prioritize safety and long-term solution. The second point is ethical responsibility. Engineers must work honestly, responsible and professionally. They should give correct information and avoid unsafe construction decision. Approving project without considering subsidence risk may endanger thousands of people. So ethical engineer must protect public safety even if it increase project cost or take more time. The next point is public health and safety. Ground subsidence can cause several flooding, damage home and contaminate clean water source. This issue directly affect people's health and daily life. Engineers must design effective drainage, flood barrier and several foundation to reduce this risk. The next one is regulatory compliance. Civil engineer must follow government law, environment regulation and engineer standard during construction and planning. When engineers follow the regulation, they can help reduce unsafe development and environmental damage. Ignore rules may lead to legal action and project failure and danger to the community. The next point is stakeholder involvement. Many groups are affected by land subsidence such as government, local resident, industry and environmental organization. So each stakeholder has different interests. Engineers must communicate clearly and help all parties find practical solutions that benefit society. The sixth point is conflicting stakeholder requirement. Some industry want to continue using groundwater because it is cheaper, while communities want better flood protection and safer living conditions. The evaluation is engineer must balance economic development with environmental protection and public safety. Long-term community safety shall be prioritized over short-term profit. The second last is sustainable engineering solution. Engineer can reduce subsidence by introduce better water management system and stronger infrastructure design. So for the solution is as rainwater harvesting, control groundwater use and improve drainage system can reduce future risk and create more sustainable cities. So the last one is SEG. The project support global sustainability goal related to water, infrastructure, city and climate action. So applying SDG help engineer create safer and more environmental responsible development for future generation.
To address the ground subsidence issue in Semarang, several sustainable engineering solutions can be implemented based on Sustainable Development Goal 12, which focuses on responsible consumption and production. The first and most important solution is the implementation of circular urban water system. This includes large-scale rainwater harvesting systems, wastewater recycling plants, and managed aquifer recharge system. This solution should be prioritized because excessive groundwater extraction is the primary cause of land subsidence in Semarang. Continuous pumping of groundwater reduces pore water pressure within the soil layers, causing consolidation settlement and ground sinking. By reducing dependency on underground water sources and restoring groundwater balance, the rate of subsidence can be controlled more effectively in the long term. In addition, circular water system promote responsible water consumption, improve long-term urban water security, and support sustainable urban development policies in Indonesia. The second solution is the use of lightweight sustainable fill materials such as EPS geofoam and recycle lightweight aggregates for road and foundation construction. Semarang's coastal areas consist mainly of soft alluvial clay soil with high compressibility and low bearing capacity. Traditional soil backfill creates excessive vertical stress that accelerates settlement. Using lightweight materials significantly reduce the load acting on the soil, helping minimize long-term settlement, infrastructure damage, and road collapse risk. Furthermore, EPS geofoam can produce using recycled plastic materials, which helps reduce construction waste and carbon emission. The third solution is implementing lightweight structural system using engineered mesh timber, lightweight height-strength steel, and modular prefabricated systems instead of conventional reinforced concrete. This system reduces structural loads on weak soil layers, helping minimize differential settlement and structural instability. Prefabricated construction also improves material efficiency, reduces waste, shortens construction time, and lowers carbon emissions. Overall, these sustainable engineering solutions help reduce land subsidence risks while improving public safety, environmental sustainability, infrastructure durability, and regulatory compliance. By integrating sustainable water management, lightweight geotechnical materials, and efficient structural system, Semarang can achieve more resilient and sustainable urban development in the future.
Thank you. Now that we have proposed 3 sustainable engineering solutions, such as utilizing lightweight geofoam materials to reduce building loads and constructing large-scale pipe surface water systems, it is to stop groundwater extractions, we must critically evaluate the long-term societal and environmental trade-off. Let's start with the environmental impacts. The obvious benefit of transitioning to alternative surface water systems is that we allow the underground aquifers to recharge, which physically stops the ground from sinking. By utilizing lightweight materials instead of heavy concrete, we reduce the dead load on the highly compressible alluvial soils of coastal cities like Semarang and Jakarta. However, as engineers, we must acknowledge the trade-offs. Building massive new water distribution networks requires immense construction. In fact, a 2023 cost-benefit analysis by Prativi and colleagues highlights that shifting from groundwater to pipe surface water from source like the Jatibarang Dam is viable, but requires massive infrastructure investment that temporarily disrupts local ecosystems. Additionally, manufacturing synthetic materials like EPS geofoam relies on petrochemicals. So while we solve the subsidence issue, we must be careful that our materials still align as closely as possible with SDG 12, which is a responsible consumption and production. Now let's look at the societal and economic impacts. The cost of doing nothing is catastrophic. According to a comprehensive simulation study by the Japan International Cooperation Agency (JICA), land subsidence is responsible for up to 79% of the increased flood damage caused in Jakarta. If we don't implement these solutions, millions of people will be displaced. Furthermore, research presented at the E3S web of conference points out that land subsidence primarily destroys the infrastructure and livelihoods of vulnerable, low-income communities in hazard-prone areas like North Semarang. But there is a major socio-economic trade-off to our solutions. Cost and accessibility. Pumping groundwater is currently free for local industries and residents. Transitioning the entire city to a piped clean water supply for local industry and residents, which means the clean water supply system means citizens and industries will be forced to pay higher water tariffs, creating severe social friction. Ultimately, our conclusion is that the short-term financial burden and construction disruptions are absolutely necessary. The long-term benefit, saving a coastal megacity from sinking beneath sea level and preventing billions of dollars in infrastructure collapse, far outweighs the immediate trade-off. That's all from me. Thank you.